Okay, this is a video just to demonstrate how to resolve, to find two unknown forces when we've got a system like this, and it's got to be assumed to be in equilibrium because otherwise the process won't work. So what we've got here is the example that was sent to me that's in one of the handouts. So we've got a 30 kilonewton force downwards from right to left. We've got an unknown X force that's horizontal. We've got a 40 kilonewton force at 60 degrees below horizontal, and we've got another unknown force that's at 60 degrees to the 40 kilonewton force. So I'm going to work this out graphically and also then calculate it. So the first thing to do is we're going to need this later on, but I'll just add to the graphic a vertical axis so that we've got some relationship with this force and the vertical. So that's if we say that's horizontal, that's 60 and 60, that's 120. So therefore, this has got to be 30 if that forms a right angle there. Right. So my method of transferring these forces to make a force polygon is to use the method using a set square and a rule. And I'm going to create a force polygon where the scale is 1 kilonewton is equal to 2 millimeters. So our 30 kilonewton vector will have a length of 60 millimeters. So the first thing to do is to actually transfer that down into a bit of white space. And I've drawn this diagram accurately, so I'm just going to trust that the angles are correct. And if we measure this one out at 60 millimeters and the force is heading in that direction, okay, we've got one vector and we'll label it 30 kilonewtons. All right, next one. We'll choose the next known vector. So that's this one here. What's my best method going to be here? Maybe this way. I'm going to draw this one in long so that I can then just align my rule with it to extend it. And that's 40 kilonewtons, so we'll make it 80 millimeters. Okay, so 40 newtons. Now, we don't know the magnitude of these two forces, but we can find them by simply adding them to create a connected polygon. Doesn't really matter which one we do first, but I think that the doing y first might actually be helpful. And I can be pretty confident that this is going to head up this way because the whole thing's got to connect together. Once again, I just need to extend my line a little bit. And now this one here is horizontal. Okay, so those are our two unknown forces. We now know their magnitude and their direction. Because to be in equilibrium, the vectors are going to follow each other. And I'll just tuck that in just so that it's clear. Okay, so what are the magnitudes? So I've got 116 millimeters. So it's going to be 58 kilonewtons. And 47, so 23 and a half. Right, job done, we've found them. And we now know that if we transfer the sense back, that this x vector is pushing towards the joint or the point of coincidence, and the y, we can put an arrow on there, that's upwards. So I quite like the graphical method. It's to me, it's quite a simple way of doing things, and for a lot of things, it's accurate enough. And if we did it using CAD, it would be absolutely accurate. The other alternative is to calculate, and you will be asked to do that sometimes to produce a diagram, a force diagram, and then um, validate it by calculation. So if we say the sum of all the forces vertical is equal to 0, what are they? So if we look at the 30 kilonewton force, it's got two components. It's got a horizontal component and a downwards vertical component. So downwards is negative. So we can say that this downwards component of the 30 kilonewton force is 30 sine 30, because it's the opposite angle of this leg of the triangle here. So minus 30 sine 30 degrees. And then the x has no vertical component, so we can ignore it. And that's why it's better to do the verticals first. And so for the 40 kilonewton force, that's 60 degrees. So we've got the sine of 60 degrees is going to be the component that's downwards. So that's, once again, it's negative. So minus, and down is negative, minus 40 sine 60. And the vertical component of y must be, and this is why it was useful to draw that line in, is 30 degrees is the angle to the vertical, and it'll be y cos 30 degrees. So calculating those out, we've got 30 sine 30 15 minus 15 minus 40 sine 60 34.64 plus, and you can say that cos 30 is 866 y. Right, so minus 15 and minus 34.64, 34.64 plus 15 equals 49.64. Now I'm going to transfer these over to the other side of the equals, and that will make that a positive. So 49.64 equals 0.866y. Therefore, y is equal to 49.64 over 0.866 equals, divided by 0.866 equals 57.32 kilonewtons. Right, so that's Y, and the sum of the verticals is the y cos 30. So y cos 30 is equal to 49.64. And if we created a triangle here on this vector, this isn't very accurate, but it'll do. We have a horizontal and a vertical component there. Mine's not that accurate, but yeah, but it's a few millimeters out, but I didn't really measure those angles, so it looks like it's right. But that's one way of just validating what we've done, and we can also say that the horizontal component of this vector here is going to be somewhere in the region of maybe 30. Anyway, let's see how we go. So, sum of all the horizontals is equal to 0, equal to, so we have, if we start again at the same point, we have 30 cos 30, and that's also negative because it's heading from right to left, minus 30 cos 30. And then we can just call it x, and we know it's a minus, but because we've already figured that out. However, then we've got another, well, this is a positive, so we've got plus the 40 cos 60, and we've got positive y sine 30. Almost ran out of paper. Okay, once again, putting some numbers against that. $25.9. Eight. Well, we're going to call that 26. And we don't know what x is yet. Plus yes, 40 cos 60, 20, and y sine 30. And we know what y is now, so plus 57.32 sine 30. 28.66. So we can say, we'll just do the maths and leave it with minus x, or we can take that x and put it over here, and that way we can also determine that. So it creates a positive number, which is useful. So minus 26 plus 20 plus 28.66 equals 22.66. Okay, so kilonewtons. So if we just check it to our drawing, yeah, it's sort of in the ballpark. So, 23.5, 22.66. Yeah, that looks right. Okay, that's the process. So, hopefully that's useful. And and we could have created a polygon here that was a somewhat different shape if we'd have done things in different order. If we'd have started with the 40 kilonewton force, we would then have put the 30 on and created something that was the inverse of this. But it doesn't really matter. They all work. But when you've got two unknown forces, you want to have your known forces, draw them first. All right. Hopefully that's useful. Cheers.